Now we're going to talk about gears. Gears are essentially like a screw. It's a type of transmission. And always like any machine element, Newton's laws prevail. Friction, parasitic air motions, all these factors that affect any other kind of machine element affect gears. Gears have the added interestingness of the actual shape of the contact profile of the teeth can have a huge effect on life, sound, and dynamics. As you see, gears come from microsilicon gears. This is the hairs on some sort of bug. This is a very complex geared mechanism. This was done out at one of our government laboratories. Chains of gears for driving wheels. Whole selection of different types of gears shown from a manufacturer's catalog. Okay, so the gears are fundamentally based on something called the involute shape. What the involute shape is achieved by if you take a piece of string wrapped around a circle, and as you unwrap the string, if you were to hold a pen on it, it would trace out the shape of this arc of this tooth. Who came up with this? Was it Dr. Involute? No one's really exactly sure. We know it wasn't Leonardo because Leonardo drew his gears with just round pegs engaging. And if you just have round pegs engaging, they wear out very quickly because there's too much sliding. What the involute shape gives you is a very, very special feature. And that is if I have one gear and another gear, the effective contact radius of the two gears happens at what's called the pitch circle, which is roughly what's going about through the middle of the tooth. This is a spur gear shape formed by this involute. There's other specific types, but nominally they're all based on this unique property you're about to see. And that is, if the gears are moved apart a little bit, it doesn't matter with respect to what the transmission ratio you'll get is. The transmission ratio of any two gears with involute teeth is such that transmission ratio equals the number of teeth on gear 1 divided by the number of teeth on gear 2. What this also tells you, by the way, is you need to have the same shape of the tooth here and here. The teeth have to be of the same relative size. Now, how big the teeth are has a huge effect on the torque that can be transmitted through the shafts, the quietness of the gear engagement, and how the mounting has to occur. And I have this. These would be what would be called face gears, but this is a nice demo here because they're really big, chunky teeth. When you apply torque or twist, watch what happens. See the way the one moves relative to another, this one slides up the other? This is called the gear tooth separation force. It's a function of the gears when they first engage at what's called the pressure angle. And when they start to push on each other, they want to push each other apart. So when the gears are rotating, the pressure angle is always there, but that force, there's a point where the force is not trying to push them apart to where the force is trying to push them apart, and it's a cyclic force. And any times you have a cyclic force happening, that's what can lead to noise. Okay? So the smaller the pressure angle or the finer the teeth are, the less separation force and the quieter the gear train tends to run. But the smaller the pressure angle and the quieter they run, the smaller the teeth are, and the individual load that a tooth can bear is less. So you use a large pressure angle to get a large tooth to transmit a lot of torque, but it can tend to be more noisy. So that gives you a range of design from very quiet gears, how you want to think of picking a pressure angle, to gears for picking big forces. Related to the size of the teeth is how many teeth on the gear. The pitch of a gear is how many teeth per inch. In the metric world, the mod of the gear is the spacing from tooth center to tooth center in millimeters. Pitch is the inverse of mod, essentially. although one is metric and one is English. It's very entertaining sometimes also to look at how the outside world looks at gears. For example, here is something that looks very interesting. It's the Manchester Metro Shuttle. 3 gears making the city work together. I'm glad I don't live in this Manchester. I won't tell you what state or country this Manchester came from. But this tells me the city does not work well together. Why? These 3 gears are all engaging at the same time. Ain't no one going to turn nowhere. It's going to just stay put. So I show you this to make you think about, be careful of how you put your gears together to make sure you actually have a system that will work with good efficiency and do what you want it to do. And we're going to dive into some of the details of how you can make that happen. So the first thing is, learn your nomenclature, pitch circle, the pitch or the mod. You're worried about the depth of the tooth, the shape of the tooth, what's called the dedendum, that's the distance from the pitch circle down to the root of the gear, the depth of the tooth. All those parameters are in the text you can read and come up on. The main parameters, remember, are the pitch diameter. That's the diameter at which the gears act to engage. And the mod, that tells you the size of the tooth, and the pressure angle. That should be tuning you into the equivalent here is, this is going to equal the pitch diameter of gear 1, pitch diameter of gear 2. So I can figure out the gear ratio without knowing anything about the teeth itself. I can assign the teeth later. In general, the minimum number of teeth you ever want to put on a gear is on the order of a dozen. Otherwise, what happens is the teeth get too big and you get too much what's called undercut on the teeth, and the teeth tend to break off, which is very bad. So gears are fun. Design them well. And when you're done, remember, your product can sell. Design them bad, very sad. A gear train is what the terminology is when you have a whole bunch of gears together working. There are many different types of gears. The basic spur gears we just showed you in the earlier slide. And then there are what's called helical gears. Helical gears are a version of a spur gear, but the teeth are set at an angle. And I have a couple of really big ones here. And on these aren't that big because really big gears would be meters in diameter. But this gear here, you can see the teeth are at an angle. And if you ask, whoa, why are the teeth at an angle? Well, what it enables you to do is when they engage, and I'll see if I can pick this up to show it better. They are much smoother because they tend to make contact down, and if you look on the other side, on up. So they make contact not just straight across. They make contact through a line, and one starts to engage while the other starts to let go, and it's a much smoother, quieter motion. So they tend to be quieter and last longer. But remember we were talking about the pressure angle? One little interesting fact with helical gears, as they engage, they want to push each other apart axially. So you have to design the bearings to support them to take those additional axial loads. It's a real problem. Therefore, it could be a real opportunity. As a matter of fact, it turns out that there's something called a torsion differential, self-locking differential, no electronics. It's what's used in what the called quadratrack drives. And that is an invention that was done in the 50s. A guy named Jim Gleason did this. And it uses the fact that helical gears, when they engage, want to push each other apart. He used that self-help principle to engage the clutch on the differential of a rear differential of a car to always make the torque go to the wheel that needs it, not the wheel that wants it. So in a torsion differential, the wheel power is always going to the wheel that can take the torque and use it, not just spin on the ice. Beautiful application of self-help by using a, quote, problem to turn it into an opportunity. So look for that in the use of helical gears, how you can use that separation, axial separation force to preload mechanisms automatically. You can also take helical gears and use them of certain shapes of them to have cross shaft axes. So one shaft is moving this way and make it turn a right angle. Helical gears can do that for you too. Worm gears can give you very high ratios. Fantastic opportunities you can do with gears. This is the actual piece of a manual transmission from a car. The world would not move without gears, simply because it's easy to generate high-speed, low-torque motion from a motor or an engine, but the world that you live in generally wants high-torque, low-speed, and that's where the transmission ratio comes in, and that's what gears give you. When you have a gear train, how do you calculate the ratio? And indeed, when you have a gear train, how do you design with gears such that I can get high transmission ratios? You generally are not going to have a very high transmission ratio by putting 100 teeth on gear 1 and 10 teeth on gear 2. Or if I want 1,000 to 1, 1,000 teeth, 10,000 teeth on one and 10 on the other. You'll end up with something that looks like this. And that's not so good. How can I get very high ratios, say 1,000 to 1, by not having a monster giant gear and little itty bitty gear? Well, the answer is you use a gear train, and with a gear train, it's very simple to do things in series. It's not unreasonable to have 5 to 1 in one gear train. Or excuse me, between one large gear, which would be the large gear, and the small gear, often called the pinion gear. So for example, let's look at this gear train here and let's see what it does between the input and the output. If I have 9 teeth on this little red gear and 38 teeth on this blue gear, what's the transmission ratio between these two? It's 38 over 9 for stage 1. This black gear is attached to the blue gear. It's concentric with it. So this is 9, this is 38. And notice the way we're drawing the arrows. If this is rotating this way, the blue one will rotate down. So by drawing this kind of schematic here, you can determine if I turn the red gear this way, what's going to happen to this Mr. Purple at the end. Okay? The black or the gray gear here is attached by a shaft, so it's concentric and turns at the same velocity, rotational velocity, that the blue gear does. And it's got 9 teeth. And on the big green gear here, we've got 67 teeth. That's starting to push the relative size, and you can see the effect we were talking about, how these gear teeth start to get a little more weird looking. That's starting to push it, but it's still definitely doable. 67 to 9. This is stage 2. Now stage 3, it's interesting. When you go from green to purple, you are at 67 to 33, but it's the other way around, 33 to 67. Why would anybody gear it up just to gear it down again? It may be that this is useful, or this was just put there to make you wonder, why would anybody do that? That's silly. Why don't I just make this green guy the final ratio? Achieve the final ratio through just the green guy. But let's go ahead and calculate what's the ratio at this point. And I don't want to put the 1 to 2 here. It implies that that's the ratio. I could get my calculator out and do this, or I could say, okay, this is equal to, this is about 40. I'm going to step up here, and this is a little bit higher than 60, so this is somewhere, let's call it 2,500. This down here is 9 times 9 is 81, which is 80 for small values of 81. 2,500 over 80, this is going to give me somewhere 35-ish to 1 as a gear ratio. How close was I in my estimate? Let's look at another way. 9 goes into 38 4 times, so I'm a little bit shy. 9 goes into 67, 63 plus 1 is 7. Let's say almost 8 times. So another way of estimating this, I get 32-ish to 1. So you see, I could get my calculator out and calculate it right away, but this gives me an idea where I am. This gets back to the whole idea of appropriate analysis and learning to be quick on estimation. Okay? Pretty high gear ratio. What happens if I wanted to get that 1,000 to 1? Well, I could go 10 to 1, 10 to 1, 10 to 1, and I get 1,000 to 1 through a serial gear train. And we're going to see, so that would be, for example, big gear, little gear. And this is, it gets a little extreme on the sizes. Maybe I'll go 9 to 1 4 times. That would be 81 times 81, 640-ish. So I'd have to add another one. That's probably a little, the math is easier on that one. But you could do a 4-stage or even a 5-stage to get your 1,000 to 1. But it would end up looking something like this. How would you get 1,000,000,000,000 to 1? 1,000,000,000,000 to 1. How would you do that? We'll chew on that a little bit. We'll get that to the end at the end of this topic. There are other types, and remember this is a serial gear train. There are types of gear trains where you can put things in parallel. So in a much smaller package, you can get very high gear ratios. Remember though, every time gears engage and disengage, there is a net efficiency. And the higher this ratio is in a stage, the lower the efficiency tends to be due to the number of teeth and the way they engage gets more and more hard to do efficiently due to the nature of the geometry of the involute when you have these extreme differences in sizes. But they're still fairly efficient. You can have upwards of 90% efficiency per stage and higher in some cases, even 95% with really well-designed helical gears. Okay, so this tells you how the direction goes. So this is telling me if this gear is turning this way, the arrow is always pointing head to head or tail to tail, that the purple gear is going to turn the opposite direction. So that's how you can trace through which direction things are going. Okay, now let's do some examples of gear trains. What is this thing you hear from? Well, this comes from a FIRST robotics kit, and you can look at it and get some numbers on it. And what is this? Well, it turns out we believe this is from a washing machine transmission. Is it right? So go online and look and find out. But our question here is, what is happening as you turn this part here? And if you were to look inside here, you'd see, as I'm turning the input gear really slowly, the output gear is really moving fast. Let's see what kind of a gear train we have in here. I've taken the screws out already, so the top cover comes off. You can see the grease here. And watch what happens when I turn this input. The output moves really fast. Is that really what would happen? Or more realistically, is there actually a small motor that goes in here, very high-speed pinion, low torque, that would turn this large gear, and as the large gear turns, the output gear here barely moves. This is actually how it really works. And this is a serial gear train, much like we saw on this slide. And we have a little gear would feed a big gear, or turn a big gear, excuse me. Attached to the big gear, concentric with it, and moving at the same angular velocity is another pinion, which drives a gear that has a pinion attached to it that drives another gear, and a pinion and another gear. And notice at each step, the teeth get bigger and bigger and bigger. And that's because the speed is going down while the torque is going up. And as the torque goes up, remember torque is force times radius. So the radii are on the same order as the speed is going down, which means the force on each tooth is going up. So the tooth size has to get bigger. We have 1, 2, 3 stages to this gearbox. And how would you estimate the transmission ratio for this gearbox? Would you go in and count all the individual teeth? That would be very hard for you to do just looking at it from this camera angle. You don't have to count the teeth. You can get the good estimate for the gear ratio just by looking at the relative pitch diameters. So you have first stage, second stage, third stage, fourth stage. Each stage perhaps on the order of 3:1 to 4:1 of diameter ratio between the pinion and the gear. So if you have 4 stages, each one was 4:1, that would be 4 to the 4th power, which is what? 16 times 16, or 256:1. If it was a 3:1 ratio on the diameters, you would have 81:1 ratio. Which is it? Well, you should be able to put your ruler up to the screen and get a scaling and figure out what that gearbox ratio is for this unit. When you look at a unit like this, and now you also look at the cover, you'll notice that there are holes in the cover to which the shafts that hold the gears seat. So the gears are supported by shafts that are supported on each end. So it's a simply supported shaft. What that does is it keeps the gear tooth separation forces that we talked about earlier from causing the shaft to bend. In other words, for this gearbox, you would never have this long of a shaft from here to here with a shaft only supported by a little bit and the gears trying to push each other apart as they're turning. So this was a well-designed gearbox where when the cover goes on, it mates very precisely. The shafts line up and the outside of the cover comes together, so all the shafts end up being supported on both ends with the gears in the middle. Let's look at another example of a gear train. This is a custom designed system from a first robotics class. And actually this team, my wife's robotics team from Bishop Brady, designed this gripper such that it would reach out and grab a large diameter ball. The robot would transport it to the scoring area and score with it. And yet the robot could then pull the gripper back and tucked in tight for driving around until it acquired another ball. What's missing from this is, you tell me, is the drive pinion. And where would the drive pinion go? On this gear, touching both of them? Could it touch both of them? Does it need to? Watch what happens when I move the gears. I think you can see that if there was a pinion in there, it can only touch, in other words, engage one of the gears. It can't, and there's no reason or need for it to engage both of them at the same time. I purposely left the pinion out of here so you can imagine and draw into yourself what it should look like. Notice the size of these gear teeth. How were they chosen? Were they designed for a particular strength requirement? Should they be smaller? Which would take longer to manufacture? Should they be large such that when this machine is bolted together with relatively crude tolerances, the gear teeth would always engage and remain engaged? These are the kinds of design questions you want to ask yourself as you're building a system. And notice how the 4-bar linkage is driven by the two main gears. So it maintains synchronization between the two arms. So gears not only are used as transmissions in terms of reducing the speed and increasing the torque of a motor that's input to the system, and then providing a slower speed, higher torque output, gears can actually be used as part of linkages to accomplish a motion function. Now also note on these gears here, if I put a little timing mark, that this is the position of the gear to start, and at the end, when the gripper is closed, it's around here. So this is an arc of about 120 degrees, and actually it's 1, 2, 3, 4, 5, 6, and I cover 2 of those, so it's exactly 120 degrees. What do these teeth on this side do? Well, the teeth up here are used to engage the pinion from the motor. So one could argue that we really only need the gears to be cut over 180 degrees, or 2 half gears would work. And it turns out you can do some very interesting things with having gears that just partially cover an arc. So gears need not be a full 360 degrees around. And it turns out even that they need not always be on a circle. You can have non-round gears do some very interesting motions. So a little bit more for you to explore in the world of the fun of gears and linkages. Speaking of parallel type gear trains are what are called planetary gear trains. And the way a planetary system works is you have your outer gear or your ring gear. You have the sun, and then you have the planets. And the planets are connected to each other by what's called a planet carrier. Depending on what's fixed and what's moving depends upon what the gear ratio is. I have as options I can rotate the sun, hold the planet carrier, and let the ring rotate around it. Or I can rotate the sun, hold the ring, and now the planet carrier will rotate as do the individual planets. In a multi-stage gear train with different planetary segments, depending on which I hold fixed and which I rotate, I can get many different ratios. And indeed, the way in a car you have the transmission work for an automatic transmission is the bands in an automatic transmission. What those refer to as essentially the band brakes, remember we talked about those way back, that will alternately fix or let spin free the outer ring gear, for example. So you can do some really fantastic things with what you fix and what you don't fix and what ratios you can get. The moral of the story is that you can get some very high gear ratios in a small package. And let's look at what you can do. Let's say I have a sun gear of nominally diameter 5. Okay, and then, I'm sorry, a ring gear, nominally diameter 5. I got to fit it in this picture. And then a sun gear of nominally of diameter 1. What's the transmission ratio I can get? The transmission ratio goes like diameter of sun 5 plus 1 over 1, or a 6 to 1. And you may say to yourself, well, why is that any better than just doing this? Why would I want to go through all the complexity of having to have this machine here with these 3 planets? Well, the reasoning is, again, depending on what I'm going to hold fixed, the planet carrier or the ring gear is which motion, which ratio I get. But the more important thing is, with 3 planets, I'm actually, this tooth is engaging this planet, and this planet is engaging this ring, at the same time I can be having this tooth engaging this one and this one here. I can have 3 teeth on my sun engaging 3 teeth on the ring, so I can transmit 3 times the torque in the same package that I could that if I just had a small gear here driving a big gear. And by the way, when you have a big gear being driven by a small gear, the small gear is called the pinion, and the large gear is called the, surprise, gear. Okay? Sometimes on really big gears they're called the bull gear. With a planet system, though, you have the additional advantage of it's really easy to get multiple stages. You see, earlier, you have to start stacking things up in series this way, and you start getting some fairly strange radial shaft loads. With a planetary system, you can literally take stages such that the planet carrier, if I, in this case, have all the ring gears all in a line, and they can even be extruded from or formed all at once in an outer housing. And what you get is, here is the gear teeth of the outer housing. And then here is a planet gear. Here is a sun gear. And lo and behold, the planet carrier here comes around and it drives the next sun gear, which drives the next set of planets. So I could get 6 to 1 each stage. So in 5 stages, I have 6 to the 5th power, which equals 36 times 36 times 6. That's a huge gear ratio you can get. 36 times 36 is almost 1,500. So now you're looking at monster gear ratios. And you say, whoa, that's fantastic. But you also got to remember that every time you have a gear tooth to gear tooth contact, you may only be having 95% efficiency. And now if I'm looking at 1, 2, essentially 2 gear teeth contacts per stage, that's 12. So now I have 0.95 to the 12th power. So you may end up with a very high gear ratio, but you may end up with 50 or 60% efficiency at most. Okay? So it depends upon how precisely you've made your gears, how well you've designed them, what are the bearing supports to keep things perfectly concentric such that the teeth mesh really well and they're not doing all this kind of trash motion as they're moving, because that'll all cause a lot of loss of efficiency. But you'll find that most high ratio gearboxes in a small space will use a planetary design primarily because you get a little bit extra ratio and multiple engagement of teeth at the same time, which you won't get from a normal serial gear train. A planetary drive, by the way, is of the generic form of what's called an epicyclic drive. Epicyclic drive being you have the carrier arm, the planet, the sun, and the ring, and depending on which one you hold fixed, give you which kind of motion and which kind of gear ratio. When I say which kind of motion, I'm talking about direction. They're very straightforward to design. Many, many different combinations of these gearboxes. I think there's 12 or 13 total different combinations that people have come up with for different epicyclic drives. All of them have their pluses and minuses, and if you really are getting into designing an optimal gear train for your machine, it's well worth the while to dig deep into what the characteristics of each of them are. The nice thing is that there are modular epicyclic gear trains you can buy of many, many different types, planetary types. There are gears that, or gearboxes or epicyclic drive trains that don't even use gears. They look like rollers and hubs. In an automotive transmission, here is how planetary gears are made. The outer ring gear is actually typically formed from a piece of steel that's stamped, or what's called a process called fine blanking, where the teeth are formed by the tool, not actually individually cut. It's amazing what you can do with very, very, very high volume manufacture. Someday, go to a used car parts place, get an automatic transmission. You can tell them, I don't even need one that works. I just want to take it apart. Get a manual transmission. Take it apart. It's fantastic to see the ingenuity that people have had over the years to package something in such a small space that can take really high power from the engine, make it do things. Differentials, same thing. Go to an auto parts place, get a differential, take it apart, find how it works. Remember, we talked about differentials already earlier, and why in the context of steering you need a differential to let the wheels go around different length paths. Why do some differentials send power to the wheel you want, i.e. this torsion differential we mentioned earlier? And whoa, look at these helical gears. Isn't that interesting? Why do some gears, or some differentials, not do that, and they always send the power to the wheel that's on the ice? Is it a cost issue? What's the issue there? When you start looking at taking gears and using them in your robot designs, for example, if you're designing for a robot contest, you got to remember that you may be given modular gears, but you got to mount them correctly. You have to be very careful about where the hub is and the gear tooth separation forces. Remember, they can be substantial, and if the gear teeth are mounted so they're on cantilevered shafts, when you start pointing a lot of torque in them, the gear tooth separation forces can pry the shafts apart and the gears can skip. Okay, so for example, if you look at this system here, notice how these Delrin gears used on these shafts, the hubs, and we did this the other day and we were talking, don't do this. This particular machine that this particular person had designed in a class called me over and said, I don't understand it. It worked great, but I want to start using it. The gear teeth start skipping. Something's wrong with the gears. I want new gears. And I said, no, something's wrong with your listening. I said it a little nicer than that. When the person turned on the machine, the gears were happy. But when they put it under load, they started skipping because the gear tooth separation forces located a distance back from this bulkhead to which things were mounted were causing the whole thing to push itself apart, and the gear teeth would snap out and stop engaging. Just took these two gears, flipped them around, problem went away. Putting where the forces occur back close to this structure that resisted the force, I tightened the structural loop up, got rid of the deflection problem. Okay? Very, very important to be worried about how you mount the gears. We'll show you some more examples of that. Now, what you may have seen earlier in there was something, it wasn't the gear you maybe were thinking of. And look at the gears in the differential of the car. Gears don't have to just be cylinders. Gears can be having weird looking angles on the face like this. This is called a bevel gear. And if we go over to our uranium fishing device we showed the other day with the bead belts, we can see that we've got a bevel gear driving a bunch of small pinions. And if you look carefully, you'll notice something here that's happening. It's working nicely. But why did these students put the hub, which we just said don't do that, on the inside and the gear at the end? Why did they do that? The answer was, A, they weren't looking carefully. B, they didn't listen. C, they saw it in a catalog but not in the text. E, for this particular design, they got lucky until I talked to them, but that's all right. In that the loads on this device are very small and the shaft deflections are very low, but if the shaft deflections, if the gear really had to transmit a lot of torque, the shafts would start bending up and either the teeth would start skipping, or instead of running at the proper best contact zone, the teeth would start running near their tips and they would wear out much more quickly. So even though the design looks wonderful, if you go to actually implement this in reality, you'd want to have this front support bearings here located up real tight, right close up to where the gear shaft, the back side of the gear face is, the teeth face is. So in that case, the hub would extend in the middle. Now, sometimes there's no room between the front face of the gear and the shaft that it would otherwise intersect, and you have to put the hub behind. You just have to do that sometimes. You don't have the space. But then you calculate the gear tooth separation forces, the bending of the shaft, loads on the bearings, and you can sometimes tolerate that. While we're over here, so that's an example of bevel gears. While we're over here, let's take a look at some large spur gears. And we're going to come back to this, and I want you to look at what this device is and where did we buy those gears. Think about that. How do we get those? Okay, we'll come back to that. So bevel gears allow you to turn angles between shafts. A bevel gear allows you to have one big gear that drives multiple other shafts. Very, very powerful design tool. Bevel gears generate large gear tooth separation forces that, if you're not careful, will cause the gears to spread apart and lose contact or have premature wear of the teeth. Okay? It's amazing how many times you'll find, and these are design examples, not necessarily good ones, that I've pulled off from what other people have done in the past that show the hub, the gear, where the teeth engage, far away from the main bearing. This is such a common problem. It's one of the reasons I keep showing it, is you don't want to do that. There's no reason why this can't be reversed and the support bearing right up behind the back of the gear. Okay? Really, really important. Other types of gears is not just for rotary to rotary motion. You can have rotary to linear motion, or indeed linear to rotary motion, and that's the rack and pinion. And all a rack is, it's a gear of infinite diameter. Then the tooth shape is actually not an involute. It's a straight or trapezoidal tooth that engages with the involute on the pinion. Very, very powerful concept, particularly for long range of motion machines. Remember, the rack and pinion is something that you can't see it in here, but the shaft that holds the motor has a rack surface on it, so when I turn the handle, I can get linear motion out of the motor to tighten or loosen the belt that's inside. You can make a rack and pinion by having a rack that you've bought or water jet cut or machined. You can also lay down a chain. Remember our discussion of chains. So if I took a chain and mounted it, assume I cut the chain and I mounted it on a surface, I could then have the teeth engaging and driving it linearly. So you can make your own rack and pinion just with chain, actually. Very, very interesting, because now you can have the pinion driving up a rack of chain where the chain goes off and on the other side accomplishes some other function. So you can be very creative in many different ways. Okay? Worm gears. Worm gears are a very interesting type of gear because they are not engaging in this conjugate action that is nominally rolling contact. Remember, an involute gear shape, the teeth as they engage and disengage are that involute shape makes it so they're almost rolling. That's what gives them the very high efficiency. In a worm gear, when you're rotating it, this is like a lead screw. It's basically the lead screw principle. And here, the worm, that's the little linear spirally dude, engages the worm wheel such that when I turn the worm one rotation, one pitch, essentially this thread, it looks like it advances to that thread, or on the surface of the worm wheel, it moves forward one pitch of the worm. So watch what happens, what you can do with respect to the gear ratio. So the transmission ratio for a worm is one revolution of the worm causes a motion at the pitch circle of the worm wheel of the lead of the worm divided by the radius. Of the worm wheel. That gives me the angle I've moved through. So when this worm wheel goes 2 pi in rotation, the worm wheel goes by the lead. This should be lead here. And this is the radius, divided by the radius. Two pi times the radius of the worm wheel divided by the lead, which is, in other words, 4 pi d, pi d over L. If this was 5, and this lead was, and let's put some real numbers on this. This could be, for example, pi times 50 millimeters. And it's not at all unusual to have a lead of, say, a few millimeters, say 2.5 millimeters. It's a fairly coarse worm wheel. So that's roughly 3 times 20, or around 60 to 1 in a single stage. This is also not back drivable. This gets back to the lead screw question and the ramp and the friction angle we talked about. This gets back to the question in a gearbox. If it's very high efficiency, it's back drivable. I can do it in one stage. I don't have it very high efficiency, but it's very low cost. Now, there are a lot of different particular shapes of these engaging teeth to increase the efficiency. There have even been designs in the past where people have put recirculating balls in here, just like in a ball screw, an early patent, oh my goodness, probably 30 years ago, for a recirculating ball worm drive. Very, very commonly used, particularly in machines where you want a very high ratio and you don't want it to back drive, particularly for safety reasons. Now, when you go to design your own gearbox, how do you pick all your parameters? Basically, not just the transmission ratio, but you have to be worried about the size of the teeth, the pressure angle, the width of the tooth. You can't arbitrarily pick a really wide gear to support a huge load, because if the gear teeth aren't aligned properly, they'll edge load and break anyway. So for example, if I thought I wanted to have these two gears and I want to have a huge load transmitted, and I'm worried, how wide do I have to make the teeth so they don't break off? And if it turns out they need to be this wide, Well, you can probably align the shafts of this tooth and these teeth such that the gear teeth will align. But if the gear is really large, wide, engaging another really wide gear, and here's the bearings supporting the shafts, what happens? Well, there's gear tooth separation forces, which would cause loads across the gear, which would cause it to bend, the shaft to bend, which would mean the teeth are engaging not uniformly. If the shafts are misaligned by a small angle, that small angle is amplified by distance. This is the Abbe offset we were talking about. And you will, again, have different engagement areas of the teeth, such that there will be a point on the tooth that takes more load and it starts to wear first. It'll wear first, and that's when the whole thing cascades and starts to fall apart. How wide can the gear teeth be? Well, first of all, helical teeth are a little more tolerant. But look at this set of helical gears. Look at the width of the thickness of the tooth and the width of the tooth. That's about 5 to 1. This is where we get back to St. Vinay's principle. You can push it sometimes to 10 to 1, but as you go much more beyond that, you start having other problems associated with the gears. And the way you're going to want to transmit the high loads you're thinking of is you have to make the gears bigger and the teeth bigger, rather than just keeping the teeth arbitrarily small and the gear really wide. So this design spreadsheet, spur gears, for example, helps you go through all those inputs and outputs and sizing your gear and telling you what the separation forces are so you can incorporate it in the design of the shaft and the bearing supports. Okay, you design your gear train. It handles the loads you want, but you want to have a high precision mechanism that will perform with minimal backlash. And remember we talked about in the screws the idea of preloading. How do you preload gears? Lots of people have worked on this over the years, and you have to have some what's called backlash in the gears. You can't design gears and just push them together radially to force them engage. You can't arbitrarily, here I'll show you here. So if I have these two helical gears and they're separated by just a little bit, you can hear the backlash. That's no good. And because they're triangular shaped teeth, or involute shaped, I can push the centers closer together. So I have no backlash, no rattle. But if I push them together so I have no rattle at all, first of all, this looks really round, but it's not going to be perfect. The center is going to be offset to one side or the other. And as the gear rotates, if you happen to have pushed it together at the smallest point, when you rotate it and it comes apart, then you have backlash. If you happen to be so unfortunate to have put it together and pushed it together at the large point, when you rotate it, now that eccentricity between the bore and the pitch circle is going to really mash the teeth together and you could break them off. So you have to set your gears up with some center distance being larger a little bit than the average pitch diameters of the two gears. You have to set them up so you have some backlash. You have to use a second set of gears, and there's many different types of systems to do this in terms of two different sets of gears. One transmits torque in one direction, one transmits torque in the other direction, and they're either spring-loaded or fixed distance separation, but still preloaded by the inherent elasticity in the system to take out the backlash in gears. Many systems, the vast majority of systems, your car, for example, doesn't care that you have some backlash between the gears because you're always moving in one direction. And when you stop and go in reverse, you don't notice, you don't really care about a little bit of that backlash. In a high-precision robot or machine tool, you can't tolerate that, so you need a way to preload the gearbox. Many different ways of doing that. And one popular way for epicyclic gear trains is what's called a harmonic drive. And a harmonic drive, you can see here, what it uses is flexible elements. And the red The red element here is called the flex gear. And as the wave generator, which is the part on the inside, moves, it rotates and it deforms the flex gear. And that deformation actually allows the gear teeth to be pushed together so they do actually engage all the way. And you don't worry about this eccentricity I told you about earlier because of the flexibility of that flex gear. The teeth are very small, so you get very high ratios. The challenge is designing it so that the teeth don't strip off because they are so small, and they have to be small to accommodate that flex spline, and that the flex spline does not fatigue over lifetime of the gearbox and itself break. And that's the trick in designing these harmonic gear drives. And they can be designed very, very well, very, very low backlash because they allow that elasticity of the flexural elements to force them together. Planetary gears, on the other hand, are much harder to design with no backlash, so they use very high precision components and design it with minimal backlash. When you buy a gearbox, be aware of what is the backlash and what is acceptable or not. If you're designing and building your own, it's fairly straightforward to do the calculations in terms of how much gap do you need to accommodate the center distance errors that you may have just by manufacturing or by thermal expansion. Now, how do we model gears in CAD? You can have a very nice modeling program which then later can be used to drive, for example, a water jet cutter to manufacture the gears. There's one particular program we use called GearTrax, but there's many others you can check also. And what you look for in a gear design program is you start with inputs to it in terms of the size of your gear teeth that came from what you calculated you want to have to resist the loads, and you got that from one of your gear design spreadsheets, for example, that come with the course. The picture that the CAD tool will give you will help you to determine what is the undercut that you're happening on the teeth. So does it look like you have good conjugate action? But to generate the solid model of the gear teeth and put them together takes a lot of time. And for the final design, you may want to do that. But for the initial fast, rapid, how do I make a CAD representation of my machine? You can do that simply by drawing your gears where the outside diameter of the gear, which you need to put in there for the purposes of space and making sure that the gears fit in the box. But you overlap the teeth, and you can see here where the solid model looks like the two circles overlap, and they do, because you set then the pitch, the center distance between the gears is now set at the average pitch diameter of 1 dp2 over 2. Okay, so in other words, this is the outer diameter of the gear. This little step I drew in here shows d pitch, and you just set the center distance equal to half of the average of the two pitch diameters. And you go ahead and let, in your solid model, you let the two solids overlap in the assembly. It enables you to very rapidly create a good enough solid model of your gear train. So how do I prototype gears, or how do I actually manufacture gears that are good enough? What is good enough? Well, for fun, let's go over here and look at this device. And does anyone know what this is called? This is a ringer. You often think of gears, high precision gearboxes, hot rods, transmission ratios, helicopters. That's a place where I'm really happy that we have really high precision gears. What's good enough for a gear? These gears were made, if you could look at them really carefully, how? Were they cast? Sometimes gears are actually made just by stamped sheet metal parts that are put together. These, I believe, were just simply cast, because you can look at the complexity of why and ask yourself the question, why is one tooth 90 degrees or half pitch out of phase with its neighbors? What's going on there? What does this thing do? This is a wringer. And in the old days, people did wash by hand a lot, washboards, and before you hang out your clothes to dry, you got to squeeze the water out. So the wringer does that. But what's that got to do with these gears? And what's good enough? Well, and notice what almost happened here. I was standing near this and my shirt almost got sucked into the wringer. So there's an old expression, don't get your appendage caught in the wringer. Why is that? Well, huge forces are generated in this machine. Notice these springs here keep this upper part, let this upper part float. And now let's zero in and look. Look at what happens to these gear teeth. If you look on the ends, before I engage and suck the cloth in to wring it, there's a certain amount of overlap between the gear teeth. And also be looking at the other two gear teeth on the inside. As the outside layer of gear teeth just start to engage here, the inner set will not be engaged at all. And when I start to rotate this, see when it first engages, there's hardly any tooth contact. And the amount of tooth contact, you think, oh my God, look at that, it's not engaging at all. It's going to slip off. And it's going to jump back. But the inside set of teeth that are out of phase of it, they remain engaged. And the result is I have what feels like relatively smooth motion as I've rolled quite a thick part. So some clever person, 150 years ago or more, figured out that if you just had one set of chunkily made teeth that were too crunchy and that would skip and wouldn't engage well, I could use a second set at a half pitch away so something that is always engaged nicely. The reason that's so important is, one, this demonstrates how robust spur gears can be, but the other thing it demonstrates is that you can take relatively coarsely made gear teeth and make some really exciting prototypes and maybe even products out of them. How do you do that? Well, if you have the gear design software, you can get the actual exact involute shape you want. That generates the CAD file that then you can take to a laser cutter, an abrasive water jet cutter, particularly if you're cutting out of aluminum. You can 3D print gears. Beware of how you 3D print them, though, what the strength of the plastic is and the grain of the plastic from the 3D printing process, because that can have a huge effect on the strength of the gears. Also beware of many of the 3D printed plastics don't last real long with time. So you may make some gears from them and they work and they look good, but it's not something necessarily you want to rely on your product working for a long time, because the plastic some of the plastics tend to age not very gracefully. In one particularly effective way of prototyping gears is with a water jet cutter. And standard water jet cutting leaves a taper. And even when you select minimal taper, you'll get some taper. And that is where then the thickness of the gear matters. If you have a thin gear, it's not so much of a problem. If you happen to have one of the more advanced water jet cutters with a tilting head, you can take all the taper out and you can truly make fantastic gears. As a matter of fact, I've seen big diameter gears from a windmill yaw axis. This was meters in diameter, where they damaged the teeth. And what they did was then they cut out the old section of teeth, cut on the water jet cutter a new tooth set of teeth, bolted in. And these were teeth that are near 4 inches, 100 millimeters in terms of face width. This is an example of a partial gear that was cut on a water jet cutter. This was for one of the first robotics teams we worked with. They didn't need the gears the whole 360 degrees. They just needed partial motion of the gear driven by the pinion for a robot arm. And the neat thing about doing that is you get the co-gear out of it, which you could say, wow, that's good. I could put a pinion on the inside and remove. Or you can take this and make a picture frame out of it too, kind of a nice sunshiny thing. Never waste anything. Okay? So there you have it. Gears are fantastically fun. There's a huge amount of work to be done in the world in designing custom gears. It's constant array of new alloys come out, constant array of new types of lubricants, makes it such that every year it's easier and easier to design gearboxes in a smaller and smaller space that'll take more and more torque, which means it's getting the weight out of the machines. You get the weight out of the machines, your helicopters fly farther, your cars drive faster, further with less fuel. There's no stop to the need for just being able to design custom gearboxes and gears of better and better quality, driven often by the materials, the lubricants, and better machines to make the gears more and more precisely. So it's a fantastic field that you want to master, so you too design gears can you and do anything you want with motion. Fantastic.